Good morning, ladies and gentlemen. We are going to finish up 5.4b today. Hopefully I can shorten the length of the video, so I'm going to get right at it. Now, yesterday I said we were going to take this, or h of x. It wasn't actually, it's a full-blown function, and it can be anything other than, well, it can even be just an x, but it's a full-blown function. We said we're going to prove this. Well, what is the integral from a to h of x of f of t dt? Well, what is the antiderivative of little f of t? That would be called big F of t. And we're going to evaluate that from h of x to a. Well, what happens is if I take my upper limit and I plug it in here, I get big old F of h of x minus, this guy comes in, this is second fundamental theorem, big old F of 2. Why did I say 2? It's a. It's an A. Remember, what is A? It's the first letter in the alphabet. A, this is A is a number, okay? So we just redefined our function. Our function y actually equals big F of h of x minus f of a. Remember, a number, it's a number. And what are we doing? Hey, we're backing up the train. We're walking in our same old circle. So what we're doing is we are taking the derivative of the antiderivative, because that's what they wanted us to do. And I'll do the hard one here. That's dy dx equal, how do I find the derivative of f of h of k? It actually sounds like a composition function that we did earlier this year. And you know the derivative of big F is little f, and how the heck did I find? We've seen that before. That's like f of g of x. Remember when we did that? That's called the chain rule. Composition functions, that's a big old fat chain rule. So what do we get? We get, that's going to be f, okay, little f, or actually here, I'm gonna make it the other way so everybody understands. And I'm going to say, hey, that's big F prime with h of x in it. And then remember, we had to go back inside and we had to take times the derivative of h prime of x, the derivative of the inside function. Derivative of that, that's a number. That's just gone. And remember, dy dx, okay, we took some time here to rename big F prime as actual little f. And it's not two f's. It's actually little f of h of x times h prime of x. It's the chain rule. And we got the same exact thing as we had. Whoa, I didn't go high enough. Here, I'm going to go all the way up. We just kind of proved it algebraically. Okay? It's not magical. It's not mystical. It's mathematical. Well, what happens? What happens if there's a function on the top and the bottom? You know, I've never seen this on the AP test. This used to be in my old calc book I used to teach about. But what's it going to do? It's going to plug that in, and that's going to call that little f of h of x, because we're taking the derivative of it, right? And that's going to be times the derivative of the function I just put in there, minus, now I got to put that in there, and because that's a function, it's not a constant, that's going to give me f of g of x times g prime of x, okay? So that just means I need to input the big F of t, okay, in there. So you're going to see it, because if I actually took a second and proved that's big old F of t, evaluated from h of x to g of x, second fundamental theorem says that's big F of h of x minus big F of g of x, which means if I take the derivative, hey, I got a composition function there. So that's going to be f of h of x times h prime of x, derivative of the inside, minus, another composition function. That's little f of g of x times g prime of x. And remember, little f is big F prime of x when I'm looking at that. That's a notation we got to be comfortable with, and I understand it's new, but there we go. So let's rock and roll here. Let's take a couple. What do we want to do with this one? Well, we want to just evaluate it. Notice my lower limit's a number. So if I'm taking the derivative of an antiderivative, I'm going to have a function minus my constant. When I did that, when I take my antiderivative, I'm going to get big F of x plus some constant. So what I'm going to do is I'm going to come back and I'm going to take the derivative of this, because I don't want to continually prove them. I want to get there. dy dx is actually going to equal, well, this is little f of t, so that's going to turn into little f. Why did I write an f? Because I'm saying an f. Yeah, that's going to actually be little f, which is going to be 3x squared minus 5 times 3x squared, right? And then that's my that's going to be my derivative of that. But then, okay, I got to plug it, and remember that's a function more than x, so that's going to be times by 6, and that is an x squared, isn't it? Yep, 6x. Just going to be a 6x. So then this is, I'm going to simplify this. This is going to give me 9x to the 4th minus 9 times 5. That gives me 40. Oh, that's 5 times, oh boy, 15x squared. That's still multiplied times 6x. And when I distribute that 6x there yet, I know my dy dx is going to equal, what's that going to give me? Yes, 54x to the 5th minus 6 times 15 would be 90x cubed. There is my derivative, okay? Now, please understand, this isn't going to be the only thing you're going to be doing with this stuff, okay? There could be a beautiful extension to this problem, and a nice, beautiful extension or follow-up on this would say, at what values of x does y have horizontal tangents? Whoa, horizontal tangents, what's that talking about? Horizontal tangents, that's not the guys on the beach laying down, okay? Horizontal tangents are when dy dx equals 0. I have horizontal tangents. So what would I do? Well, I would take, if I extended it, this is just kind of a fun little problem. I'd say, hey, when are you, my derivative of 54x to the 5th minus 90x to the 3rd, when are you equal to 0? And I would probably look at this. Well, as I came through, I can see there's a GCF in here of 3, and the 6 got distributed, so I know if I'm going to factor this, I know there's going to be an 18x cubed coming out of there. And when I take an 18 out of 54, what is that? Is that 3x squared minus, when I take my 3, that's going to be a 5, right? So I can see when x equals 0, I'm going to have a horizontal tangent, and when x squared equals 5/3, or when x equals plus or minus the square root of 5/3, it looks like I got 1, 2, 3, 4 tangents, and you know, if I had to prove it, which I'm not going to do right now, then maybe it's just going to say, hey, what are the maximums, minimums? Then I could come down and I could say, okay, here's my test, here's my number line test, I'm 0 there. I'm going to say this is negative 5/3, I'm 0 there. I'm square root of 5/3, I'm 0 there. And I would take those and I would plug those tests in there and I would see where I'm increasing and decreasing to see if they're maximums or minimums and so forth. But I'm not going to do that. It's just a good extension to the problem that we could be working with. So if you want to hit pause and give the next couple a try, why don't you do that? And I'm just going to plug and chug them away in here. And just remember the instructions you're looking at here. This isn't saying find y. This is saying find dy dx, find the derivative of y. Please find the derivative of the antiderivative. Well, I'm just going to take the derivative of this. I know that's dy dx. And I know that's going to equal, well, there's my little sine, or my little f of t. So when I plug that in there, I'm going to get the sine of the square root of x squared. Okay? And then that's times by, because this guy is really x to the 1/2. So that's going to give me a 1/2 x to the negative 1/2. So dy dx in this case is going to equal what? Yeah, right. Sine x over 2 square root x. Find when it's 0. Just kidding. Okay, so that's what we're doing. Don't forget, okay, this whole part, okay, we just introduced that yesterday. This whole part is not only do we just switcheroo, okay, and this is another one. My calculator, I don't even think will find this antiderivative. I can't do it. That's why if I need the derivative of this function defined as an integral, this is my function y, and it's defined as the integral from a to the square root of x of sine t squared dt. I can take the derivative of that. I don't need the antiderivative, because even if I had it, I know it's going to spin me right back to here with that guy in there, times the derivative of that guy for the chain rule if I had to do it. Next one, moving right along. Well, I'm going to take the derivative of that, so dy dx is going to equal, well, what is that? Well, I got to take this and I got to stuff it in, so that's going to be my tangent of x cubed minus 3 times by, my derivative of 3x squared. Oh, I probably would write 3x squared tangent x cubed minus 3. That's what dy dx equals. Okay? It's kind of a switcheroo from the variables. We're just simply walking in circles. Do you like walking in circles? This next one's a different twist. This is actually an old AP question, and it's talking a lot about big F and little f and all this business. Okay, so we want to know the integral from 1 to x of f of t dt. Hey, that actually equals x squared minus 2x plus 1. What is little f of x? Okay, well, it's not too bad, but just remember the integral from 1 to x of f of t dt, that actually equals big F of x plus some constant. Okay? Big F is my antiderivative. What do they want me to find? They're asking me to find, that's not a big F, that's a little f. So they're asking me kind of symbolically here to find the derivative of this. Well, I can do that because here is that's my antiderivative. So f of x has to actually equal, okay, so if this is, let me back up. Slow down, don't get so excited. Let me back up here. So this is actually big F of x equals x squared minus 2x plus 1, right? Because this is my integral, and if it's equaling that function, this is an antiderivative. That's big old F, and it's got everything evaluated on it. And if they want little f, that means take the derivative of that. So that means little f of x, hey, that's going to equal 2x minus 2. You got to be careful. You got to read problems. You got to go slow, okay? Because that means antiderivative, and if that integral equals a function like that, that function is your antiderivative, okay? And we got another little twist here. Find the linearization of f of x if f equals, oh boy, if f of x equals 2 plus the integral from 0 to x of 10 over 1 plus dt, 1 plus t dt at x equals 0. Oh my God, it's another function defined as an integral. Function defined as an integral. Okay, this is a big, this topic really came back about 4 or 5 years ago. It's a pretty big one. And then you're like, linearization? What the heck is linearization? Oh, I remember. Linearization was a really fancy term that they tried to tell me, but Kruger told me, hey, that is simply a tangent line to f of x at some x value. And in this case, the x value we know the x value is 0. So, okay, back to fundamentals. Let's fundamentally. Tangent line. How do I find a tangent line? What do I need to write the equation of a line? Well, I need a point and I need slope. So because I need point and slope, how the heck am I going to find a point? Where do I want to know the point? Well, I already know the x value of the point, but what's the y value of the point? So f of 0 is going to equal 2 plus the integral from 0 to x of 10 over 1 plus t dt. Oh, wait a minute. Did I plug that in right? Of course I didn't. That's an x, and that means whatever x, okay, function form, whatever I plug in for x, I plug in for x. So I need to plug a 0 in there. So what is my integral from 0 to 0? Ooh. What is, if I have no horizontal change, the width of my rectangle is 0 times, I don't care what the height is, that's 0, so I know f of 0 actually equals 2. Oh, hey, I got my point. Woo! So what do I need yet now? Now I need to know what my slope is. Well, thank goodness. Thank goodness for the second fundamental theorem of calculus, okay? Because that tells me if I need the slope, I keep grabbing the wrong pen. What the heck are you doing here? If I need slope, slope's a derivative. If this is f, I need to find f prime. So if I do that, hey, isn't f prime of x, the derivative of f of x is f prime of x, equals the derivative of 2, it's 0, plus, what's the derivative of the integral from 0 to x of 10 over 1 plus t dt? Oh, that's the antiderivative. Then I take the derivative. Oh, that's just 10 over 1 plus x in it. So f prime of 0 is actually going to equal 10 over 1 plus 0. Oh, f prime of 0. Look at there. My slope is 10. So f prime of 0 equals 10. And if I know my slope and I know a point, I know you guys are smart. You can linearize this thing real easy, and you can do it in any way you want. If you want to go in and say y minus y1 equals m times x minus x1, and say y equals 10x plus 2. Ooh, wait a minute, they wanted that linearization. I better show them what they want. That was my L of x function equals 10x plus 2. We have just linearized that function defined as an integral, and we could use that linearization to approximate the function, okay? Now we got 3 more to go here, and the next thing is we are going to construct a function in the form of y equals the integral from a to x of f t dt plus c that satisfies the given information, okay? This has been showing up more and more and more on the AP test, okay? And what they're going to do is they're going to say, hey, I got a derivative for you here, and that derivative, you are not going to be able to find the antiderivative of it, okay? And they want to know They want me to construct a function that's going to satisfy the given information. They want me to write a function. They want me to write a function defined as an integral. Okay, that's what they want me to do, because I do not know how to anti-differentiate that. Okay, well, let me back up. What are you talking about, Kruger? Well, you guys you've done this already, okay? So let's say I had dy dx, and dy dx equaled 2x minus 5. And, well, I know the antiderivative of that. Well, that's y equals, well, that's going to be x squared minus 5x plus some constant c. And if they want to say when y equals 0 and x equals 8, that's at the old point, 8, 0, right? So y is 0 when x is 8. So all that's really doing is saying, oh, okay, I can calculate that constant, because y is 0, x is going to be 64 minus 40 plus c, and this is going to give me 24 plus c is 0. Oh yeah, c has to be negative 24, so they could say y equals x squared minus 5x minus 24. Hopefully I did that right. But notice, they're going to give me a function I cannot anti-differentiate, which means all this business over here, thanks, but it's gibberish. It doesn't help me. So what do I need to do? I need to be able to construct a function defined as an integral. So I can say this really easy. Okay, I can say my integral, my y, is going to equal my integral from e to the t times tangent t dt. We are undoing what we did before. Okay, the only thing I need to know is that when I plug 0, my upper limit's always going to be an x, by the way, and it's the bottom one that I really need to know. Okay, and I need to know when I plug an x, a particular x in here, what this is saying is if I plug 8 in for x, I need y to equal 0. Okay, so what is that going to be? What am I integrating from where to 8 to make that integral equal 0? Well, wouldn't that be from 8 to 8? So this is really, they're giving me my a value because I don't care what y is. This, I'm defining y as an integral, and if I integrate it from 8 to 8, it's going to output 0. So there's my function. This is like an initial condition that they give up here. They're telling me when I put in an 8, I'm going to get out a 0. It's an initial condition. And they're going to have lots of initial conditions for us at different times. Okay? What are we doing? We are backing up the train. We are going exactly in reverse of what we did half of yesterday and the beginning of today. We're just backing things up. Well, let's try another one here. Okay? So they want me to construct a function that satisfies the given information. And what they're going to do is they're saying, okay, here's my derivative. I don't know. I can't find the antiderivative of ln sine x plus 5. Think about it. When did we ever take a derivative that we had an ln come out? It's non-integrable. I can't do it. I can't find this antiderivative. But I can define it. I can say y. If I anti-differentiate dy dx, I get y. And I can define this guy as an integral of ln sine t plus 5 dt, okay? And y of 2 equals 3, so that really means when x equals 2, y equals 3, right? It's just kind of a weird notation we don't like to see. It's really the ordered pair of 2 comma 3. So just remember when you're writing your function as an integral, this guy always, your x is always going to go on the top. And 99% of the time, your x value that they give you, your x value is going to go on the bottom. Why? Because now it's saying when I plug 2 into this function up here, I need y to equal 3. And what is the integral from 2 to 2? What is the value of that? The value of that is 0, isn't it? I need it to be 3. I need the value of y to be 3 when I plug a 2 in there. How am I going to do that? Just like that. It's going to add a 3. That's my initial condition. And I'm just adding it to my function. Okay? This is what I need it to equal when it comes out. I can define this function as an integral just like that. Notice, my variable, when I'm doing a function defined as an integral, my x always goes on top. The x value that they give me it's my a value. The y value they give me gets added outside the integral. Why? Because when I come up here and I replace, hey, come on. When I replace my x and I evaluate that little bugger and I plug a 2 in there, oh. I want that integral value to be 0 so I can tell it what to output for me. That's how I write a function defined as an integral. Isn't that sweet? Okay. Last one, multiple choice, number 91, 2015. Calculator part. If f prime of x equals cosine x squared, that's why they put it there, because they know you're not going to be able to find it. And f of 3 equals 7. What is f of 2 equal to? They had choices for you. Well, what does that mean? Because I cannot find the antiderivative, I want to define my function as an integral. Okay? I want to define that as an integral. If I anti-differentiate f prime of x, I get f of x. It's going to equal. I can't find the antiderivative of that, so I'm going to define it as an integral of the cosine t squared dt, because it's a derivative, okay? Why? This is f prime, that's a dy dx. I can throw my dy dx over there, and or my dx on the other side, but I need a different variable. Remember when we built our area functions, we always use t. And I also know that when x equals 3, y equals 7. So when x equals 3, a value. So when x equals 3, okay, my a value is 3. But when I actually come up here and I put a 3 in there, what's the integral from 3 to 3 of cosine t squared dt? This is 0. What do I need it to equal? I need it to equal 7. So I'm going to say plus 7. Okay? So I just fingered out here f of x is going to equal 7 plus my integral from 3 to x of cosine t squared dt. Now there's a reason why this is on the calculator portion, because they wanted us to find what is f of 2. Well, it's going to be 7 plus the integral from 3 to 2 of cosine t squared dt. What do you equal, you dirty, rotten scoundrel? We grab our calculator. We say, I don't know, what does 7 plus the menu of a 43 from 2, no, let me get to the right page here because I already forgot my function. From where are we going? We're going from 3 tab to 2 tab of my cosine t squared tab dt, and I'm going to give it the old control approximate. It's 6.759. 6.759. And guess what? 6.759 was one of the choices. Right? Now, why do I say, and I'm pretty confident in this, that if I did a menu 43, and I did a tab and another tab, and I went to a cosine, and I went to a t squared tab dt, and I hit enter, see my calculator can't even integrate cosine t, cosine x squared, cosine t squared. It doesn't matter what variable you put in there, just so you know that. Oh yeah, but Kruger, you put a t in there. We're looking for a cosine x squared. And it don't matter. Okay? It does not matter. It does not matter. It can't do it. So because it can't integrate cosine x squared, please don't expect me to do it because the calculator is much smarter than I am. Okay? Hey, that rounds us out for today in 5.4b. Hopefully it made a little bit of sense. If it didn't, please reach out to me. I'm not even going to get into that. So, you guys, I hope you have a great day, and I hope you thoroughly enjoyed playing math for yet another day. Have a good one, bye, guys. Talk to you later. Bye.